So in this lecture we just continue with the spectral theory. I would be happy if we get this done today, but I think there's a little bit too much, just a tiny bit too much to get finished today. Now as I'm recording this, I'm probably much faster than I am in the lecture when I write everything on the board. So I have a strict plan where I want to finish so that the material fits exactly in one lecture. But this might mean that the video is actually shorter than an hour and 20 minutes. So I will cover the rest of 7.3 on adjoint operators, and then I will do 7.4. In the end of 7.4 there's an example which I will still do, but then I think the summary then I do next time. Let's just recall what we did in the last lecture. So we talked about the adjoint operator A star, right? And here I remind you of the relationship between AX, which lived on the dual spaces, and A star, which lives on the Hilbert spaces. And then we had these beautiful formulas about the range. So the orthogonal complement of the range of A is a null space of A star, and vice versa as well, as long as the range is a closed set. Okay, let's move on. So now we talk about symmetric operators. Let's look at this definition here. A is symmetric if AUV equals UAV for all U and V in the domain of definition. And we call it self-adjoint if the domains are the same. If the domain of A star is equal to the domain of A. Yeah, let us consider an example down here. So A is minus Laplace on L2, where omega is a smooth domain. And we have Dirichlet boundary conditions. And I use as domain of definition all functions in H01 and in H2, which have the boundary U at the boundary of omega is 0. Actually, I would not necessarily need to write this down here, because this is already in the H01, right? This is already part of the 0 thing there. Okay. So then we compute UAV, which is the integral of omega U Laplace V by definition of A. Oh, and I lost the minus sign right here. Cool. So minus. And then we do integration by parts. We get a plus. And so then we keep the plus. Then we do integration by parts again. We get a minus sign. And then this is A. So here I need to add a minus in my notes. Okay. So then A star is A. And we can choose the domain of a definition. That's just the same. So we get a self-adjoint operator. So let us look at the next example, 7.3, right here, where the operator is just the first derivative, d by dx, on L2R. Domain of definition is H01R. And then we can do a similar calculation by integration by parts. So UAV is the integral of uv prime dx, which is then minus integral u prime v dx, which is minus AUV. So here we actually do get a minus sign because we do integration by parts only once. So we could say A star is minus A with the same domain of definition, and then this is called a skew adjoint operator right down here. So symmetric operators have a beautiful spectrum, which we come to in a minute. But before we get there, here is a little proposition which I need to prove first. And this has to do with the inverse when we have a lower bound for the operator A. So let's assume A from x to y is a linear surjective operator, which is bounded below, so that AX is always larger or equal delta x, which is larger than 0 for all x in omega. Then A inverse exists and is bounded. Allow me to make a little note here, just because the norm sign on the norm of x is a little bit wrong. I need to do the typesetting better. Let's prove this. Here's the proof. Since A is surjective, for each y we can find a pre-image x. So we can find an x so that ax equals y. And this x we call actually A inverse y. So that's just a definition of x, is just a new symbol. But now we want to show that A inverse is actually a wonderful, beautiful linear operator with a bounded operator norm. So then I do a to the minus 1 in the operator norm. I write down the operator norm with the supremum over y. A inverse y divided by y. And I know y is actually ax for some x, so I can replace y with ax on top and bottom. And A inverse A cancels each other, so we get the supremum x divided by ax. And then I estimate this is less or equal as if I take the infimum over the bottom. But based on the assumption on the lower bound on A, the infimum is still bounded by delta. The infimum is bigger than delta, so 1 over the infimum is less than 1 over delta. So, the inverse is well defined. We have a bounded operator. And when we have two values x1, x2, which both map to y, then their distance, as you can see here, is equal to 0. So then A inverse exists and is a bounded operator. Ah, beautiful. Now this has a beautiful corollary, 734. So if A minus lambda I is invertible and bounded below away from 0, then we can find the resolvent, and the resolvent is also bounded by 1 over A minus lambda I. So this was the last ingredient we need for the spectral theorem of symmetric operators, which is here. So we consider an operator ADA, which is densely defined, symmetric on a Hilbert space. And then we have the following 4, or is there a 5th? No, there's just a little gray bracket. So the 4 conclusions. AXX is real. All eigenvalues are real. Eigenvectors to distinct eigenvalues are orthogonal. And the continuous spectrum is also real. Remember, the continuous spectrum were those where the resolvent exists but possibly be unbounded. The proof actually is surprisingly easy because we have done a lot of work already, in particular in the previous corollary where we estimate the resolvent. Let's do it. So, on a complex Hilbert space we have AB is BA complex conjugate. So then we can apply this to A. And then we get the conjugate of AXX is the same of XAX. So just using the conjugation. But then by symmetry this is also AXX. And there we go. So this thing must be real. Remove those boxes. So then secondly, if I have an eigenpair, I'm sure you know immediately what I mean by eigenpair, right? I mean to have an eigenvalue lambda and an eigenvector or an eigenfunction phi. So that's an eigenpair. Then we can write a phi, comma phi to be lambda phi, comma phi, which is lambda phi square. So this is also real. So we are done with that too. Let's get rid of this. So these are the first lectures, so I still need to get used a little bit to all this machinery here. But this will become quicker as we move on, I'm sure. All right. So where are we at? Third. Yeah, so if we have two eigenpairs, phi 1, phi 2, to different eigenvalues, lambda 1, lambda 2, then these eigenvectors or eigenfunctions must be orthogonal, and you compute this. Lambda 1, phi 1, phi 2 is a phi 1, phi 2 is phi 1 a phi 2, which is lambda 2, phi 1, phi 2. So this means either lambda 1 is lambda 2 or phi 1 times phi 2 is equal to 0. So this takes care of this. And then the last one was the result on the continuous spectrum. So let's first of all compute a minus lambda I for lambda written in components. So I write lambda to be, so write down here, gamma plus I mu, where gamma and mu are real numbers. And I would like to show that mu is equal to 0. So then the continuous spectrum would be in the reals. So we compute a minus lambda ix in the norm squared. We have an inner product, so we can write it explicitly as ax minus gamma x minus I mu x for the first term, and ax minus gamma x minus I mu x for the second term. So then we have 3 terms here times 3 terms there, so we get, if we multiply this out, we get 6 terms. No, we get what? 3, what do we so anyways, we get these following terms, ax minus gamma x times ax minus gamma x. Then we get the I mu term there, and the gamma term, and the I mu term, and the I mu term twice, and the I mu and the A, and the A and the I mu, and the gamma and the I mu. Okay, so these are all the terms. The first one is ax minus gamma x square in the norm. The next one is I times mu x gamma x. And then we have an I gamma x mu x. But the one term is minus here and the other term is plus, so they will cancel. And then similar for the A terms, we have a plus I mu x ax and a minus I mu x ax. And axx is real, so we can flip the A to whichever side we want, so then these terms cancel as well. And then we keep the gamma square x square term there. So what we keep is ax minus gamma x square plus mu square x square. Now, if mu is bigger than 0, then this operator a minus lambda I x would be bounded below, away from 0. Right? For each x we would be bigger than mu square norm of x. But then by the previous corollary, 734, the inverse resolvent lambda a exists and is bounded. But this means that lambda is not in the continuous spectrum because these were points where the resolvent is unbounded. So we got a contradiction, so lambda cannot be positive, and we must have lambda is equal to 0. So then we are done with this bit as well. Perfect.